1, 1. If t is 1, where are you? 1, 2. That should give you some confidence that we've done it right. But convert these to parametric equations, because these aren't parametric equations. So the parametric equations, I'm going to continue right here, so I'm going to erase. What are the parametric equations that we will use for C2? X of t is 1. That's what you were saying, right? And then y of t is 1 plus t, right? And t is between 0 and 1. I will point out that these t's do not have to be between the same values, okay? Whatever you're doing on this curve, you can have t between anything. It doesn't matter. But whenever you do line segments, we will always have 0, 1 if we do it the way that I've shown you. There are other ways to do it, but I think this is the cleanest way. Any questions? All right, you ready? We're going to set up the integral. I don't know if I'm going to evaluate it or not. Any other information that you might want to get now before we set up the line integral? You want to do derivatives now? Because we're integrating with respect to arc length, aren't we? ds. So we're going to need the derivatives. We may as well get them now. So over here, what's dx dt? 1, and then dy dt, 2t. Over here, dx dt, 0, and dy dt is 1. And now we crank it out. All right, the line integral over c of 2x ds is equal to the line integral over c1 of 2x ds plus the line integral of c over c2 of 2x ds. Let me just point something out. This is a lowercase s. Later on, that will be an uppercase s in a different section. It will be surface. Right now, the s means arc length. So when I do it later, I will exaggerate it. I'll be like that for capital S. All right? Okay, so now just think we're good. Okay? I think. I don't know. This first one over C1 is going to go from, what's my limits of integration here? 0 to 1, 2 times x. But what's x on C1? T. So 2t. And then ds, but ds is the arc length formula. So square root of what? Dx dt squared, so 1 squared is 1 plus 2t squared, so 4t squared dt. That's your first integral. Second one, so plus integral 0 to 1. 2x again, so this time 2 times x is just 2 times 1, so 2. And then square root of 0 squared plus 1 squared is 1. dt. How would you do this first integral? Just a u sub? What would you use for u? 1 plus 4t squared? Because the derivative of that would be 8t, and you'll be off a little bit. So this is a basic u sub. We'll move on. I won't get the numeric answer for that. What do y'all think? Seem okay? Where? It was 2 times x, but x was 1. In that parametrization, x was 1. So it is 2 times 1 here. Yeah? Okay. Raglan. Raglan. Could you leave, please?
Yeah.
Thank you.
I can do that.
Okay. Thank you.
Sorry.
That's all right. You can sleep out in the hallway. Okay?
Yeah. Thanks.
Okay. Have a good one. Hope you feel better. All right, so there are some other line integrals that come up. It's not something that we can see yet. We'll see it in the next few sections that we will use these. It's the line integral along the curve C, so it's the same thing we had before, but this time with respect to x, not arc length. And the only thing that changes in the formula is that this is dx instead of ds, and that makes it a lot easier to do because this part's the same, but instead of having to do square root of all that stuff squared, what you're basically doing is this. You're doing dx dt squared plus dy dt squared. And when you're doing it with respect to x, what you're assuming that you're basically taking dy dt to be 0. That's what you're doing. You're saying that what you're basically saying is that this change, y is changing as a constant, so the derivative, or the y function is constant, so its derivative is 0. That's what you're doing. And then that zeroes out, and you just get this, and that's this part right here. So x prime of t is dx dt. That's all it is. And then when you do the line integral along the curve C with respect to y, you're doing the same exact thing, except you're treating that as the 0. That zeroes out. Okay. Now later on, okay, in later sections, we will use this as part of what's called Green's theorem. And so just so we get some notations straight, if you take the line integral over the curve C of p of xy, now p is just the name of the function. Like we've been using f of xy, capital P later will be just the name of some special thing. Capital P of xy dx, so that's the line integral over C of the p function with respect to x, plus the line integral over C, so same C, of a q function, not the same function, with respect to y. Then the notation here is that we put them together. Now it doesn't look like there's a lot of difference in those two, right? But this would most of the time be considered bad notation if we didn't clarify that this means two separate integrals. Because you have, with respect to x and then with respect to y, you should have an integral sign in there or something. And this is saying that when it's not there, this is what we mean. So it's purely just a notation thing here. All right. I'm going to give you a few minutes here. Let's see if you can come up with parametrizations. I mean, this is not super new, but it is a little different. Well, no, I don't see anything different now. I think about it. But you do it. The first parameterization should be easy. The second one, I just want to make sure you understand how to do that. Oh, top half, yeah. That's obvious that I did not. I know the difference between half and half. Thank you, though. Somebody raise their hand when they have both of them, just so I can get an idea of when people are finishing. Okay, so I'm gonna kind of write them up here, let y'all keep working. Kieran, do you see what I'm saying? Yes? Okay. You could do that. It's just a little more work than you need to want to do.
What? Oh, I see. Okay, -1 to I. I see. I got it.
So C1 is going to draw the upper half of the circle, right? That goes like that. C2 connects what? -1, 0 to -2, +3. Notice I put little arrows on there to show like the direction of motion here. Like when I start t at 0 to pi, it goes like this. And then I want to go from here to here. Who has my y and x and y for the line segment? Who wants to volunteer that? Go. No, what? -t - 1. I don't know. How many agree? Yes? Okay. If we have enough people agree, then it's right. All right. So we have our two parametrizations. Yes? No questions? Yes, the 2 points, R, the R thing, and R naught and V and all that. Okay, so we'll need some derivatives here, right? We'll need some derivatives. We're going to be doing what's dx dt with negative sine t, dy dt on this one, cosine t. We may not need it, but I mean, it's not that much for us to get them, right? We are going to need some of them, yeah. So dx dt is -1. dy dt is 3. We good? No questions? Let's set up this integral, because notice that line integral is a little different than the ones we've had, right? The ones we had were with respect to arc length. So I'll need your help here because I'm about to erase this if I can't remember that. This is going to be the line integral over c of sine of x dx plus cosine y dy, which by the fact that we're splitting it into two segments is line integral over c1 of sine x dx plus cosine y dy, plus the line integral over c2 of sine x dx plus cosine y dy. So I have to split it up into two line integrals. And I still need more room here. This is equal to integral from where to where? So I'm on C1, so 0 to pi. Sine of x, so sine of what's x? Cosine t. So it's sine of cosine t. I've got composition of a trig function into another trig function there. And then dx, what's dx? Negative sine t. So I'll just put the negative out here, times sine t dt. Is that okay? Now, I could, if I want, keep going, all right, and do the cosine part here, or I can split this into two different integrals. I'm going to do it in two different integrals. So I'm going to say plus integral 0 to pi, and now I'm going to do the y part. Understand? All right, cosine of y is cosine of, what's y? Sine t times dy. dy is over here, cosine t. Do y'all understand where this is all coming from? Yes?
I see a difference in notation. There's in your previous slide.
Uh-huh.